Okay, does everyone have this problem wrote down that would like it? Have it wrote down. Okay, we will come back to this in just a moment. Okay, so this problem is based off of what I'll call a real life situation, and I can't remember if I saw this live on with college football or not. So does anyone know what a sooner is? Not sooner or later, but in college sports, what is a sooner? Okay? So, this had happened, I don't know when this took place, but we're always making calculations on, well, not always, but sometimes we make calculations on some of these real life scenarios. Okay.
Oh my goodness. Watch her ability to roll. When she hits the ground, nice roll. That's what they teach you in jiu-jitsu, Joe. You got to roll. Jeez. Use your shoulders. Hopefully nobody was hurt, including the horses. It was a nasty spill. That lady's falling off the wagon.
You're okay. Suck it up.
Now there's a giant rut in the field as well, where the carriage was dragged behind the horses. Oh my goodness.
Sometimes I see some of these mascots.
Girl is flabbergasted.
The buffalo in Colorado is the scariest thing I've ever seen.
Me too.
Wow. That's where you play. Now they got to fix the turf. Stomp it down a little bit.
I mean, let's hope everybody's okay. That was
I hope so.
That was a.
Jenny will check to see.
And in the pregame, Ginny rode the schooner.
Let's try it again.
It's scary.
No, we've seen enough replays, and you also got to take into account falling from that type of a height. It's possible to have parts of the body that get broken. Now, it's just human nature to think it's always funny when it happens to somebody else. Okay?
Oh, when it happens to us, it's even funnier.
All right. So, in this case, like we had just talked about, all right. So it probably wasn't moving this fast, but this is where this problem comes from. Okay? So what we see happening here is after you've read the problem, what is the next thing you should do? So what do we know in this problem? Okay? Okay? What else? Okay? So I heard velocity, not only that, but also initial velocity. Okay? What else do we know? Okay? Okay, now, this is saying how much force, okay? And I understand we know this is a force also because it says 42,000 newtons, but it says the wagon will flip if this much force is on that turn. And just because we've seen that in that video, I guarantee you, some people it will flip in an evaluation, other people it will not. But in this case, we're asking to calculate the force and compare it to 42,000 newtons. Okay? So do we have everything that we need in this problem? Okay, we need the final velocity, which is, and I keep asking yourselves these questions because, again, you are responsible for this on your own. I could just stand up here and just write this out and just solve it and just say you're on your own. But I don't think that's a good way to approach that. So what variable are we missing? Yes, I understand VF. So what is the value for VF? Okay. And then again, that's what we're solving for. How much force? Well, we don't know. So what two things do we need to know to solve for any force? Okay. And of course, you're looking at this and saying, well, we've got our mass, but what are we missing? Yeah, we're missing our acceleration, but we can calculate that, which means, I don't know whether you write this in here as a question mark. That's entirely up to yourself, because you know you have to solve for that. So what does the formula tell you to do to solve for acceleration? Okay, so we want to do this. Then again, when you have all this information here, you don't have to go reading through the problem. That's probably the 18th, 19th, maybe 20th time that we have said that. That's why this is so important. Once you get it to that phase, we know your final velocity, which was 14.15, okay, and then minus our initial velocity, which was 7.15, okay. So if I'm not mistaken, that will give us a nice round number, but this one won't, okay. So then, in this case, we had said 7. 7 divided by 1.8 would give you your acceleration, and our acceleration is approximately what? 5.93. Okay. And then that is labeled as what? Meters per second squared. I was talking with another staff member, and he had said that when he was in school, or excuse me, or other staff members when he was working in another school, if you didn't do this, you didn't label it, it's wrong. Just say, I don't know what you're doing. Just say, if you're not going to label, anything you do beyond that is wrong. I think maybe that's a little harsh, but I don't think it's asking too much effort for you to label your answers. And for those of you who do this, when you put a box around that, that speeds up the correcting process so much. And for those of you who are doing that, I really appreciate that. Thank you for doing that. Okay? Because rather than trying to find all this information here, when we're reading through these problems, you got to take into account we've got 22 people in here. Okay? So on any given paper, especially if it's double-sided and there's 4 pages, okay, that is quite a bit to read. 4 pages times, that's 88 pages we got to look through. Okay? So when we do this, that just speeds up that process that much further. Okay, so we've got our acceleration. What is the next thing we need to do? Okay, so our acceleration times our mass, which means, again, we don't have to look up there. We've got 745 times what we just calculated, 5.93. And what is our force then? Okay. 4, so we did that early. 4417. Oh, so it is. Didn't have my glasses on. That's my excuse. Now, what did they? do with them? Are they over here? Yes, the computer is in the way. Yes, you get 4,417. Okay, so once we take that off, 4417.85 newtons. So what does that tell you? What's that wagon going to do? It's going to flip over. Okay, so these things do happen. Okay, and as we saw, that's that problem was based off of something that really did happen. Okay, so let me start with this. Back row, are we on the bus? Middle row, are we on the bus? Front row. Okay, because as we see moving forward on tomorrow and Wednesday, again, you're responsible for this content on your own. Okay? Some of you do cooperative learning. That's great. But again, you're responsible for this on your own because we want you to be successful when you get older. Because I don't have it wrote down for Thursday's A&P class or zoology's A&P class or even organic chem's A&P class because that's a junior and senior level class. Those individuals are taking the ACT test, okay? And with that, we want them to score, obviously, as high as they can. The higher score you get, the more scholarships you get, okay? So why do some of them students do so well? Because they place so much time and effort into this, okay? So only you can decide, I'm doing everything that I can. Some of you are, and maybe some of you aren't. That's only for you to determine. That's not for me to answer. Okay? I just base these your grades off of the input that we get from your performance on evaluations and daily work and homework, I guess you could say. All right. So, moving forward then, we don't have a whole lot of content left to go over. If I'm not mistaken, it is just a couple of forces. And okay. So I will hand back your vocabulary evaluations here in just a few minutes. Okay. This one had kind of surprised me because we went over all three of Newton's laws, correct? So what was our explanation for Newton's first law? Inertia, right? Didn't we talk about race cars on a racetrack? Does that sound familiar? Yes? No? Kind of? Okay. We said, and I know this is true because I don't get the name of Speed McQueen or Lightning McQueen or whatever. Okay, see? You already know what we're talking about. So in that case, his advice that he receives is you have to turn the wheels to the right to go left. Okay? And the reason for that is Newton's first law of inertia. It wants to push that racetrack or that race car right off of the track. That's Newton's first law. Newton's second law then, okay, deals with gravity and a mass that's involved to calculate forces, or F equals ma. Now, in the definition in the back of the book, it might state it just a little differently, but it's basically this formula. Because on your vocabulary evaluation, it said for Newton's second law is acceleration equals the net force divided by the mass. So it's the same formula, okay? But it's just a different way of writing it. But if you wrote it down in the back of the book, the way that it says, I was a little surprised that we had received or got that one wrong. Then the third law might have been a little tricky, but we had said for individuals who go hunting, if the butt stock of that rifle, shotgun, or whatever, if that is not on your shoulder, if there's a gap in there, what's going to happen when you pull that trigger? It's going to kick back into your shoulder, because once you pull that trigger, the firing pin goes off, you have a round of ammo going down the barrel. Okay? So that is moving in this direction, but because that's not up against your shoulder, that's going to come back in this direction. That's why we talk about that as an equal and opposite reaction. Newton's third law. Okay. So, moving forward again. Okay, I think we've talked about this. So, new content, static friction. Okay, we saw the video with Egyptians building the pyramids. Okay, so how did they move? We theorize they moved those really heavy blocks of sandstone. Put it on what? Put it on a sled. Well, what would you think if there was only 5 people pulling that sled? Is it going to move? No, because that results in what type of friction then? What does it say here? Static friction. Okay? There's just not enough people. Okay? Then what happens if we add 15 more people? Okay? Well, now you got 20, and then now there might be enough power involved to pull that sled along. Okay? Enough force is applied, and will continue.
I just popped in my head when you said power. That's what I thought.
Okay? So it will continue if enough force is applied to overcome the friction. So again, that's sliding friction. Now, I often, well, not often wonder, but just think, okay, if they actually had the concept of the wheel to put on a sled. And as we can see here, what's that going to do to the friction? Is it going to increase or decrease? It's really going to decrease. And that if it decreases, it's going to become way more efficient. Okay? So with that, it could be such an aspect of, I don't think you'd, what I want to say, have the time frame cut in half building that pyramid, but changing that friction from, we can see, sliding to rolling becomes way more efficient, because it says it makes it much easier to push and pull. And I would agree. What would it be like if, unfortunately, your vehicle has 4 flat tires and you try to push it? Is it going to be very easy? You could if you had enough force, but it's not going to be very easy. But if those tires are inflated, make sure your transmission is in neutral and that the parking brake is off. Because if the parking brake is still on, that's not going to make any difference. But I think we are all individuals that put the vehicle in park, shut it off, and just keep on moving about our day. Maybe if you have a manual transmission, maybe that's when you use a parking brake. But regardless, okay, having that rolling friction really, really decreases the amount of force that you need. Okay? So again, makes it much easier to push or pull. Okay, and then must not have anything to write with that, either that space, but we just have this and then that, and I bet you we're just about done. Yep. Okay. So let's see here. If we're looking Oh boy, I think Mr. Johnson has that white Ford truck, and then I see the Bumblebee is sitting next to it, whoever drives a yellow golf cart, okay? So, I don't know, I just call it a Bumblebee, okay? So, which vehicle weighs more?
Probably the Ford.
Probably the Ford. It's got a bigger mass, right? So if it has a bigger mass, well then there's going to be more gravity acting upon that. Okay? So that's what gives objects their weight. The heavier an object is, it's because it has a larger mass. Gravity has a larger effect on it. Okay, we're about at 22 minutes. We'll have something to view after this, and then that will be it for today. So, does anyone possibly remember how many forces did we discuss or view on here last Friday? Was there 1? Was there 2? Was there 3? Was there 4? Was there 5? Was there 6? There were 4. Gravity, okay, is this basic force that explains Newton's theory of relativity. Larger the mass, the larger it's going to weigh because of gravity. Okay? Then when we talk about subatomic particles, that's what keeps these electrons in orbit. We saw that on Friday. The electromagnetic force. And then there's just 2 more. Okay? The strong force and that of the weak force. For those of you who take general chemistry, it's kind of where physics and chemistry kind of overlap a little bit, and that's where you hear that term quantum mechanics. Okay? So we do discuss that a little bit in the chemistry class. All right. So that does it for this chapter. And what I would be led to believe, I still need to update from what it says on plan book to what's over on that board. And we will be wrapping this chapter up really soon. Okay? So tomorrow you have a problem-solving evaluation. All right? It says Problem Quiz Chapter 3, Part 1. Same thing on Wednesday then. Okay? So again, if you have any issues or any problems, please find someone to talk to help work through these problems. Okay, so I said we'd have something to watch, and we're going to do that for the rest of the time. So, yes, I will go ahead and stop there. We will catch up to you next time.